Alrighty, welcome to 8.3 Infinite Geometric Series. So this one's kind of a cool section. We're building on last time. Last time is about series. Okay, so series is kind of the adaptation of sequences. Sequences 1, 2, 3, 4, 5. Series 1 plus 1 plus 2 plus 3 plus 4 plus 5. Okay, but series have a strictly multiplication pattern, at least the ones we're dealing with. Take, for example, this guy here, 2 plus 4 plus 6 plus 8 plus 32 plus 64, blah, blah, blah. The pattern here we can see is times by 2. So 2 to the n is what's happening each time. And then we're adding all those up to get a series. What's really cool about some series is that some series do this thing we call converging. There's converge and diverge. You may have read the series Divergence. Not really exactly the same thing, but yeah, that's where it comes from, okay? So there's two options, basically, with a series. Either they diverge or they converge. Diverge is boring. This is just get bigger forever, okay? 2, 4, 6, 8, 10, or sorry, 2, 4, 8, 16, 32, that's going to diverge. It basically just keeps getting bigger. Bigger, 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 bigger. You're going to get bigger forever, okay? It never really settles on anything. Converging is kind of the opposite of that. Let's take, for example, so on the next page you can write all this down. Let's take, for example, a dollar bill. Okay, so we have a dollar. And then we're going to add to that half. So kind of thinking back to Brad and his mom, but kind of the reverse scenario. Instead of doubling it, we're going to cut it in half. Okay, so maybe it's a fee that he owes her or something like that. And we're going to cut it in half. So plus half of that, 50 cents, right? Let's do this in... I don't want to write dollar signs all over the place. So let's just do this in $100 pennies, and then the next would be 50 pennies, right? Half of that's going to be 25 pennies. So we're going to add 25 pennies. And then we're going to keep going. You got 12.5 pennies. Yeah, that's where pennies kind of breaks down because we only really use half. But if we could, that would be our next one. And then we keep going, 6.25 pennies, and dot, 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 right? As we get into more of this minuscule part of a penny, though, does it really matter anymore what we're adding? If we go to the 100th day and we have cut down a penny 100 times, I'm going to crank out a series formula real fast, right? So S100 here would be 100 times 1 minus 1/2 to the 100 over 1 minus 1/2. You do that, you get... You get 100. No, I'm sorry. You get 200, okay? Is that really going to change much between 100 and 101? You plug in 101 to this one, you would get 100 times 1 minus 0.5 to the 101. You get 200. If you do both of those, you still get 200. Why is that the case? Because the thing you are now adding on is so tiny, it's not changing anything. That's still just going to be 200. It's going to settle at 200, right? This 1/2 times, or 1/2 times itself 100 times is such a small fraction that it's not changing the value of this sum anymore. I'm going to settle at about $2, okay? And so this is kind of what we call converging. After a certain point, it no longer matters that you're adding things because those things you are adding are so small, they're infinitesimal, they're tiny, they don't matter, okay? So we can say it just converges upon this number. Now, there's a really easy and quick way to tell which ones are going to converge and which ones are going to diverge. Diverge, you have r's that are bigger than 1. Okay, now we got to be technical about this. Technically, it's the absolute value. So as long as you're multiplying by a whole number, then you are going to diverge. So -1, you'll also diverge. -20, you're still going to diverge. It's just going to be a really, really big negative number. So the negatives have the same argument. But anything that's over 1, or under -1, you're going to diverge. It's the fractions that converge. The fractions, those are the ones that converge. We'll say between -1 and 1. Okay, as long as your r is somewhere in between -1 and 1, you will converge to something. That makes sense. If you look at our last problem, we were timesing by a half. A half is definitely between 1 and -1. It's a teeny little thing. And as we multiply it, more of it, it gets tinier and tinier. The only numbers that get tinier as you multiply more are fractions. So fractional ratios, not every single fraction, but fractional ratios between -1 and 1, those are the ones, the teeny itty bitties, they're going to get so small, we don't care anymore, they're going to converge. Okay. What do they converge to has a formula as well. You hopefully by now recognize this one. We just used it today again. The sum formula, right? What happens is as you go up, you get so, like this part of our formula gets so small, it no longer matters. And we end up with that. Okay, so we basically just kind of rip out the exponent part. It doesn't matter that we have a 100th term anymore. It's just going to converge to that. Okay, and that's what happened with the dollar bill example up here. I plugged in 101, it didn't change anything because we took out the part that has the 101 in it. So if you find that it does converge, you find that you have an r between -1 and 1, you get this formula for what it converges to. So let's try that out now. Head on over to the next page. We can see we have a bunch of them here. We are going to determine which of these first 5 even have sums. So let's look at this first guy here. 5, 10, 20, 40. What is the constant ratio here? Clearly timesing by 2. 2 is outside -1 to 1. This is just going to keep getting bigger. This does not have a sum. This is divergent. This diverges. Okay, and you can say diverges, you can say doesn't have a sum, that's fine as well. I find that saying diverges helps me remember that I'm done. Done, right? All right, cool. 16,842, that is dividing by 2, aka 1/2. Oh, this one does have a sum. This is going to converge. Why? Because 1/2 is between -1 and 1. Cool beans. All right, down here we've got... Oh, sorry, totally lost my place. 6 to 2, we are dividing by something. What that thing is, it looks like 3. Let's just double check. Here to here, 2 over 1 to 2 over 3, also dividing by 3. So we've gotten a ratio of 1/3. We get a convergent. All right, cool. Next one, interesting, a couple decimals here. What do we see? We get here to here, that's pretty easy to see. 1 times what equals 0.1? That would be 0.1. Let's just double check though. 0.1 times 0.1. Yep, 0.01, that's definitely the ratio. Is 0.1 between -1 and 1? Yes, because we'd also see it as 1/10. So, definitely convergent here. Now we have to be careful. There's one example here that's not here that I would really wish it was. I would like you to write down 12 over 7 plus 24 over... Nope, not 24, sorry. 48 over 21 plus 192 over 63. Okay, is this series convergent? You may be really, really tempted to say so because it's got a fraction ratio. We can see that something is multiplying each time. What is that ratio though? That ratio from here to here, we timesed by 4. From here to here, we timesed by 3. The ratio is 4/3. That, even though it's a fraction, is not between -1 and 1. Even though this thing is a fraction, it's still going to keep getting bigger and bigger and bigger. Those fractions are over 1. They're going to keep adding. And so this is in fact divergent. It doesn't stop. It doesn't have a sum. Okay? So beware of fractions. We're not saying that all fractions mean convergent, but the ones that are in between -1 and 1. So 2/3 is fine. Right? 5/8 is fine, but it's the ones that are over, so 4 over 3, 12 over 19, right? Or not 12 over 19, that would be less than 1. 19 over 12, that would be greater than 1, right? When in doubt, you can convert it to a decimal. If you see it's over 1, you're good. All right, so now what do we do with it? Find the sum for each of the sequences, or series, pardon me. Find the sum for each of the geometric series. Let's first make sure we even can. This one is going down. Looks like by 1/2. Yep, so it turns out we are going down by 1/2. Now it doesn't tell us when it wants us to stop. It's not supposed to, because we're trying to figure out where it's going to settle, right? So let's not fall back into our routine of last time. I don't have an end here. You're not looking for an end here. You're trying to figure out what the thing at no matter what. Eventually, it's always going to be this thing. So we don't need an end here, but we do need an A1. That would be 4, because A1 stands for first term. And then we get Sn equals 4. I'm sorry, Sn equals A1 over 1 minus R. Remember, that is our new our infinite geometric series, our infinite geometric series formula. The reason it's different, we've taken out the exponent part. We don't care about the exponent part. Now we have all the pieces. 4 over 1 minus 1/2. We get 4 over 1/2. That's 4 times 2, or 8. Okay, so we get 8. Now that was also throwback to rationals and some complex rationals, so if you need to buff up on that, you're more than welcome to. Any of the teachers can help you with that as well. All right, let's do another one. Does this one even converge? Let's see. First off, it's going down. That doesn't necessarily mean, it has to, but maybe it does. What is it going down by? I don't know. Let's go from here to here. How do I get a 3 over 1 to a 9 over 7? Well, this I'd multiply by 3. That I'd multiply by 7. So is it 3/7? Could be. Let's do 7 times 3/7. Yeah, that equals 3. Okay, cool. So the ratio is 3/7. Is that less than 1? Yes, that is definitely less than 1. Our first term was 7. Let's go ahead and plug those in now. Okay, 1 minus 3/7 may sound complicated, but if it's all 7/7, then I'm left over with 4/7. In other words, change that so they have a least common denominator. We get 4/7 multiply by the reciprocal, 7 times 7 over 4. This one's going to converge at a weird number, 49 over 4. Cool beans. That's where it's just going to settle out at, 49 over 4. Okay, let's try another one. More fractions. Woo! I'm going to switch colors because I'm getting bored of pink. Okay, and I'm getting bored of purple too. Let's do red. Nah, too much. Blue. Okay, weird OCD moment for me. What is the ratio? Does this even converge, right? Does it converge at all? Let's see. Well, I can't really see the ratio individually, but I can see on the bottom it's not changing, so it's 1. On the top, it's going down, so it's timesing by 1/2. It looks like our ratio is 1/2. Let's see. Oh, you can hear my son. He's very upset. 8/3 times 1 over 2. Yep, 4 over 3. Cool. So our ratio is 1/2. That means it's still going down. All right, our first term was 8/3. And so our series would be 8/3 over 1 minus 1/2. Okay, we can clean this up a little bit. 1 minus 1/2 would be 1/2. And then we can do times the reciprocal. Looks like 16 over 3 is where it's going to converge. Cool. All right, one last thing we're going to do with this is just kind of a fun, a theorem that kind of tricks people. You may have heard this before. There is a proof that 0.99999, repeating, actually equals 1. And no, I don't mean it's rounded. Okay, it's not actually, it doesn't round to 1. It actually is 1. Okay, I'm going to show you that with 0.7 here. You're going to get to see it again on your homework. It works the same way with 0.7 and 0.21. But so any repeating decimal you can do this for. So we're going to change this to 0.9. Okay, now what does that mean, 0.9 with a line over it? It means 0.9 repeating, right? So we have 0.9, 9, 9, 9, dot, 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 forever. Dot, 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 forever, that sounds like a sequence. That sounds like a series. So I'm going to split this up. 0.9 plus, take out that part, 0.09 plus 0.009 plus 0.00009, right? Dot, 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 dot. And you can see this has suddenly become a series. This is how digits work, right? If I say the number 354, I have 300 plus 50 plus 4. So I'm doing the same thing here. I'm splitting it up by digit, right? And then I actually get a series out of it. I get all of these added up together. This number just happens to keep going. Cool, so now if I treat this like a series, I say what's the ratio? The ratio here from 0.9 to 0.09 would be a decimal place of a tenth, because that's how digits work, right? We have a base 10 number system, so our ratio, the thing we're moving each time, is 1 decimal place or a tenth. Now if you don't believe me, divide 0.09 by 0.9, you're going to find 0.1, which is 1/10. That is definitely less than 1 and greater than -1. So we have a convergent series, what we have. That convergent series is the first term of 0.9. We are going to run out of room, of course. We'll go up here. Our sequence is, our series is then going to converge the same way any other series is going to converge via that same formula, 0.9 over 1 minus, since the other one's in decimal, let's just make this one decimal, 0.1. 0.9 over 0.9 actually equals 1. And so we can say without a doubt that 0.9 repeating is the same thing as 1. Okay. It's what we call a pure math trick, right? Is there a lot of practical application of this? Probably not. But if you find that fun, you may be thinking in a pure math abstract. It may just be that we haven't found a lot of practical application for it yet. But we do find, actually I take that back. The quantum level has some stuff that we've been doing stuff with stuff like this. But we can do it for any number, not just 0.9. Let's try it with this 0.21 now. How does it work for 2 decimal places? Let's take a look. I am so into blue. Okay, purple. I can split this up the same way. This is the same thing as 21, 21, 21, 21, 21, dot, 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 right? That's what that means, that line over it. And now I can split it up, maybe not by the tens place, but the hundreds place, right? The hundredths place. 0.0021, because I already used the first 2 to make 21. So now I'm going to have not 3, but 4, 0, 0, 0, 0, 21, dot, 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 right? If I had a 3-digit number, I'd have to take 3 zeros for each time I move down to kind of compensate for all of those numbers already being used. All right, so then what would be our ratio? Our ratio would not be a tenth. Our ratio would be a hundredth, because we have to move 0.001. Nope, just kidding, 0.01. The 2 decimal places. You can also write it as 1 over 100. The 100th place. Okay. We may want to go with a fraction for this one because I don't think we're going to get a nice even number of 1. We're going to get a fraction out of this guy. So let's take a look at our first term. A1 was 0.21, aka 21 out of 100. Right? If we make that a fraction, we just move the decimal place back twice. In other words, a percent. And then we can fill in our SN formula. 21 over 100 minus 1 over 1/100th. Don't panic. 1 minus 100 out of 100, take away 1, would be 29 over 1 times 99 over 100. And then if you recall from complex fractions, those match, those cancel. So we get that our rational is 21 out of 99. Booyah. All right, and that's kind of how you can create any repeating, non-terminating decimal, this huge horrid thing that we have, into a nice fraction. So maybe like a computer could read it, would be really, really helpful. All right, that was 8.3. That kind of closes out our series part of the chapter. The next thing we're going to talk about is after your quiz, we're going to head into volume. Both of these will be on the unit test, though, so make sure you keep up on both. But I say good luck on your quiz, and I will see you again in 8.4.